Welcome to the Deep Dive, where we cut through the noise and get straight to the insights that matter. Take a moment and just look around you. Your smartwatch, maybe that smart speaker responding to your voice, traffic sensors invisibly managing congestion, even, the security camera quietly watching over your home. They're all packed with smart technology, tiny digital brains trying to make sense of the world in real time. But here's the fundamental challenge, the thing that keeps many of these devices from being truly intelligent and autonomous. How do these gadgets, often running on really small batteries, perform complex AI tasks? Like learning and making decisions, without constantly needing a recharge or overheating and potentially failing. It's a huge, often unseen hurdle that's kind of held back the dream of truly ubiquitous, intelligent technology. For this deep dive, we're zeroing in on a groundbreaking breakthrough that tackles this exact problem head on. We'll be exploring some cutting edge research from a paper titled Multiplierless MP Kernel Machine for Energy Efficient Edge Devices by a brilliant team Nair, Neff, Chakrabarty, and Thakur. And this isn't just like an incremental improvement, it feels more like a radical rethinking of how we build AI at the very edge of our networks.
Okay, let's unpack this a bit. Imagine your smart doorbell not just spotting a package, right, but actually learning on its own what a typical delivery looks like, maybe adapting to different couriers or even recognizing familiar faces, all without sending a single byte of sensitive video data up to the cloud. Or picture a medical sensor that doesn't just monitor your vital signs, but learns your unique physiological patterns over time, spotting subtle changes that might indicate a problem right there on your wrist. The dream of truly intelligent, autonomous edge devices is incredibly powerful. It offers benefits ranging from, you know, unparalleled privacy to instant response times, which are vital for safety-critical applications. But as we just hinted at, there's been this enormous fundamental hurdle, the sheer energy and computational power traditionally required for machine learning, especially for the learning part, not just making predictions.
And what's truly fascinating here, and often overlooked, is how fundamentally most machine learning algorithms, the ones powering everything from complex image recognition to subtle decision-making, rely on operations that are incredibly resource-intensive, particularly multiplication. Think about it. A typical neural network, or say a support vector machine, makes millions, maybe billions, of calculations to process even a single piece of data or make one prediction. These mathematical operations, these seemingly basic arithmetic steps, are the very backbone of modern AI. But when you try to cram that backbone onto a tiny battery-powered chip, well, that's where it becomes AI's Achilles heel. This paper directly confronts that bottleneck with an approach so novel it almost sounds contradictory. The promise, basically, is to introduce the idea of a multiplierless machine learning system.
Multiplierless.
Yes, you heard that right. Machine learning without multiplication. When I first heard that, it sounded a bit like trying to build a car without wheels.
Right, yeah.
It's a radical departure from traditional digital computing, which, has historically been optimized for performing multiplications as fast as possible. This new system isn't just about making existing AI run a little better. It promises to be dramatically superior in terms of power, performance, and area, the actual chip space for edge devices. This isn't just efficiency. It's really about enabling entirely new applications that were previously impossible because of these severe energy and size limitations. It's about taking AI out of the data center and truly embedding it everywhere.
A multiplierless AI system, that's a huge claim. It really makes you stop and think. So let's delve deep into why this seemingly basic arithmetic operation, multiplication, is such a monstrous problem for these tiny power-constrained devices in the first place. And maybe to set the stage, let's first clarify what we even mean by edge computing and why it's become so crucial in our, increasingly connected world. The edge device dilemma, why multiplications are a problem. So let's start with the edge itself. We hear edge computing thrown around a lot these days, but what exactly does it mean in this context for our listener? Imagine you're at the very periphery of a vast digital network, the edge, if you will. Instead of your smartwatch sending all your heart rate data to a massive data center hundreds or thousands of miles away for analysis, the device itself, right there on your wrist, processes that data. It could be on a tiny sensor, a camera, or the device's main processor chip. It's essentially bringing the computation out of the faraway cloud and into your hand, your car, your home, or even into remote industrial machinery.
Yeah, bringing the brain closer to the action, basically.
Exactly.
And the implications of this shift are pretty profound and far-reaching. It's transforming not just how we interact with technology, but also how our infrastructure operates. When data is processed locally, at the edge, you get real-time decision-making. This is absolutely critical for applications like autonomous vehicles, where, a fraction of a second can mean the difference between avoiding an accident and, well, not. It drastically reduces latency because the data doesn't have to travel to a distant server and back.
Right, those milliseconds matter.
They matter hugely. For self-driving cars, it's immediate hazard detection. For critical medical monitors, it's instant alerts about a patient's deteriorating condition. For smart factories, it might be predictive maintenance preventing costly downtime. And furthermore, edge computing significantly increases the autonomy of devices. They can operate more independently, which is vital for, say, remote sensors in agriculture or environmental monitoring, or in systems where continuous cloud connectivity might be intermittent or just unreliable. This autonomy also translates to enhanced privacy. Less raw, sensitive data needs to be sent to the cloud, reducing the risk of breaches, misuse, or even mass surveillance.
That's a big one.
It is. For instance, in a smart home, your video doorbell processing package detection locally means no constant stream of footage leaving your property. For auditory event detection in homes, it means sounds are analyzed on device, maybe only sending alerts, not recordings, preserving your family's privacy. This fundamental shift is making our devices not just smarter and faster, but also more secure and robust, enabling intelligence in places we never thought possible.
That's a really compelling case for edge computing. I mean, it sounds like a no-brainer. So if it's so beneficial, why haven't we already made all our devices super intelligent, capable of learning and adapting on their own? What's the heavy hidden cost associated with trying to put traditional machine learning architectures onto these tiny edge devices? There must be a catch.
You hit the nail on the head. There's definitely a catch, and it's a big one. The most common, powerful machine learning architectures used today, even when they're optimized for edge applications, are still typically based on things like deep neural networks, DNNs, and support vector machines, SVMs. Now, while these are incredibly powerful for tasks like image recognition or pattern detection, they come with significant energy efficiency challenges, both for inference. That's when the model makes a prediction, and actually even more so for learning or training, which is when the model adapts and improves. Traditionally, the workaround has been to train these computationally hungry models offline, usually on massive energy-guzzling server farms in the cloud. Then, once trained, they optimize them, or compress them, for deployment on edge devices. This optimization often involves techniques like pruning.
Like cutting off bits of the network.
Exactly, like snipping away unnecessary connections, like dead branches on a tree. Or sparsification, which makes the computations less dense, kind of like turning a solid block of concrete into a honeycomb structure.
But even with these clever optimizations, specific limitations persist. For DNNs, achieving truly robust training often requires full precision floating point arithmetic.
Meaning lots of decimal places. Yeah, imagine needing to do calculations with, say, 10 decimal places of accuracy that demands a lot of bits and a lot of processing power. It's incredibly resource intensive. And DNNs also generally need large amounts of training data, which might simply not be available on a specific edge device operating in isolation or even in its local environment. While you can compress DNNs into more energy-efficient variants, like binary or quaternary networks which use only 1 or 2 bits per weight, they still face significant hurdles during the training phase. That makes real-time adaptation and on-device learning really, really difficult. SVMs, on the other hand, are actually quite robust even with less training data, and their convex optimization nature makes training more stable and interpretable. They're also excellent for detecting rare events, which is common in many IoT applications where you might be looking for an anomaly, like a specific type of fault in machinery. However, the fundamental problem remains. SVMs, like many other ML architectures, including DNNs, still rely heavily on matrix vector multiplication MVM operations. This is the heart of most machine learning computations.
Okay, so this is getting to the core of it. What you're saying is that MVMs, these matrix vector multiplications, are at the heart of SVMs and other ML architectures.
Yeah.
And those operations are the core computational bottleneck because they are such energy guzzlers. It sounds like multiplication itself is the villain of our story here.
Precisely. And let's quantify just how much of a villain it is. The paper cites some compelling data that truly lays bare the stark difference in energy consumption between different types of arithmetic operations. For instance, using a common semiconductor technology, like 45 nanometer CMOS, an 8-bit multiplication operation consumes approximately 0.2 picojoules of energy.
Picojoule. Tiny.
Incredibly tiny, a trillionth of a joule. But when you're doing billions of these operations, it adds up really, really fast. Now, compare that to an 8-bit addition or subtraction. These consume only 0.03 picojoules.
Wow, that's a huge difference.
It's nearly 7 times less energy. To put that in perspective, imagine multiplication is like driving an SUV that gets, I don't know, 10 miles per gallon. Addition is like driving a scooter that gets 70 miles per gallon. You cover the same ground, but at a massively different fuel cost.
Okay, that makes sense.
And simple shift and comparison operations, they consume even less energy. And remarkably, detecting an overflow or underflow in a digital register consumes virtually no additional energy at all. It's essentially a free check. This stark, almost shocking difference highlights the core of the problem. If your machine learning algorithm is constantly performing multiplications, it's going to be inherently power hungry. It'll quickly drain batteries and generate significant heat. For devices that need to run on tiny batteries for extended periods, maybe in a remote sensor, or operate in thermally constrained environments where active cooling just isn't an option. Multiplication isn't just inefficient, it's the absolute enemy.
The enemy.
Yeah. This fundamental constraint is precisely what makes the idea of a multiplierless system so utterly revolutionary and, frankly, essential for the next generation of AI.
It's genuinely mind-boggling to think that such a seemingly basic arithmetic operation, something we learn in elementary school, could be the biggest barrier to advanced AI being pervasive in our everyday devices. It's like discovering that the gas pedal on your car is also the biggest drag on its efficiency. So if multiplication is the problem, the logical next question, and the truly exciting part, is how on earth do we get rid of it without just breaking everything? 2. A multiplierless marvel, the margin propagation MP kernel machine. Here's where it gets really interesting, the part of the story that sounds almost like science fiction. What if you could perform complex machine learning tasks, making predictions, and even learning, without any multiplication operations at all? That's the paper's central audacious innovation. They propose a kernel machine architecture that fundamentally removes this energy-intensive operation, not just by optimizing it away, but by designing it out of existence. It's not just about optimizing an SUV to get slightly better mileage. It feels like inventing a completely new form of transportation that doesn't need gasoline.
It truly is a paradigm shift, as you said. This isn't a minor software patch or some clever circuit trick. It's a reimagining of how we implement machine learning at a fundamental hardware level.
Yeah.
The concept involves entirely foregoing complex multipliers and instead relying exclusively on what they call more fundamental but energy-efficient and optimal computational primitives.
Okay.
We're talking about basic additions, subtractions, simple shift operations, which are just bit manipulations, and the detection of register overflow or underflow. These are operations that consume orders of magnitude less energy, require much simpler and smaller hardware logic to implement, and are inherently faster. The aim is to achieve the same, or at least comparable, machine learning capabilities with a drastically reduced energy footprint, making advanced AI practical for even the most resource-constrained edge devices where space and power are measured in, like millimeters and milliwatts.
Oh, that's a bold claim. Maintaining accuracy while ditching multiplication. It sounds like magic. So what's the secret sauce behind this margin propagation, or MP, approximation? How do you make that mathematical magic happen without losing all the precision and intelligence?
The margin propagation, or MP technique, is indeed the core innovation, and it's quite elegant in its simplicity. It's essentially a piecewise linear, or PWL, approximation approach. Interestingly, MP approximation was originally proposed for analog computing systems, those old school continuous voltage circuits.
Right, voltages instead of ones and zeros.
Exactly. But this work has brilliantly optimized and adapted it for modern digital edge computing platforms, specifically field programmable gate arrays, or FPGAs. These are versatile chips often used in prototypes or low-volume edge devices. At its heart, MP is a clever way of approximating what are known as log-sum exponential, or LSE functions. And here's the critical link. These LSE functions, in turn, can effectively approximate inner products.
Inner products. Remind me.
Sure. In simple terms, imagine you have two lists of numbers, say the features describing a cat and the features describing the dog. An inner product is a way to calculate their similarity or correlation by multiplying corresponding numbers in each list and then summing them up.
Got it. Involves multiplication.
Exactly. It's a foundational operation in many machine learning algorithms, and fundamentally, it involves multiplications. So by approximating the LSE function with MP, they can essentially sidestep the need for multiplication when calculating these crucial inner products. To give you a slightly more simplified mathematical concept without getting bogged down in equations, the paper shows how an inner product, typically represented as WTX, weights multiplied by inputs, can be expressed as a difference between two quadratic functions. More importantly for this work, it can also be very closely approximated by these LSE functions, which then, through the MP technique, can be approximated using only additions, subtractions, and simple thresholding operations.
Oh, well.
These MP-based approximations rely only on these hardware-friendly operations. For example, the max operation, which simply means taking the maximum of a value in zero, is incredibly easy to implement on digital hardware by just detecting if a register has underflowed below zero. These basic energy-efficient operations are the core building blocks of their entire multiplierless system. The researchers also provide compelling visual evidence of how well this approximation works. Figures in their paper, like 2b, 2c, 3a, and 3b, use scatter plots and graphs that clearly show that for smaller values of the operands, the numbers being processed, and the MP approximation, much like the LSE approximation, closely matches the behavior of actual multiplication. For larger values, it naturally saturates or caps out, which is actually similar to the effects you see with finite precision in any digital system anyway. The key takeaway from these visuals is that there's a strong, almost linear correlation between the true inner product and the MP-based approximation. This demonstrates that this method maintains a surprisingly high degree of fidelity, even with such a radical simplification. It's not a perfect match, but it's remarkably close where it counts for machine learning. They also introduce a crucial element called Girdo, pronounced Gemma.
Gamma.
Yeah, which acts as an important hyperparameter. Think of Giro as like a tuning dial for the MP function. This parameter directly impacts the MP function's output and plays a crucial role in the learning process, allowing the system to be fine-tuned for optimal performance across different data sets or tasks. It's a key piece of the puzzle that makes the approximation both efficient and accurate enough for real-world use.
So the mathematical groundwork is incredibly clever and seems solid. But translating that theoretical elegance into actual working digital hardware, whether it's an FPGA or eventually a custom chip, that's a whole other challenge, right? How do they actually implement this MP function on digital hardware in a way that truly avoids those costly divisions and multiplications? Because just saying no multiplication isn't enough, you still need to perform the calculations somehow.
That's where the engineering brilliance truly comes into play. It's a testament to practical hardware design. The MP function, in its raw mathematical form, often involves division. Now, division circuits, as you probably know, are almost as power-hungry and complex as multipliers.
Right, another energy hog.
Exactly. So to make it completely hardware-friendly and multiplierless, they compute it iteratively using a well-known numerical method called Newton-Raphson recursion. For those of us who haven't touched numerical methods since college, imagine you're trying to find the bottom of a valley in a dark, foggy landscape. Newton-Raphson is like having a guide who at each step tells you not just which way is downhill, but precisely how steep it is, so you can take a more accurate step towards the bottom. You don't get there in one go, but you get there very quickly by taking progressively better steps. In this context, the system continuously refines its estimate of the MP function's value over a series of these iterative steps. But here's the really clever shift trick. The division operation in each Newton-Raphson step, which would normally require a complex and power-hungry divider circuit, is completely eliminated.
Eliminated? How?
Instead, it's replaced by a simple right-shift operation. They achieve this by quantizing the denominator of the division, essentially rounding it to the nearest upper bound of a power of 2. For instance, if the mathematical denominator is, say, 7, they don't perform divide by 7. Instead, they round it up to 8, which is 2 to the power of 3, and then divide by 8 becomes a simple energy-free operation. Just shifting the bits of the numerator 3 places to the right.
Wow, that's smart.
It is. This is implemented in hardware using a priority encoder, which efficiently identifies that power of 2 exponent. It's an ingenious shortcut that maintains accuracy while dramatically simplifying the hardware. This iterative Newton-Raphson approach offers significant efficiency gains because it converges very quickly to the desired solution. The paper demonstrates that for the proposed algorithm, only a limited number of iterations, specifically 10, are required in practice to achieve sufficient accuracy.
Only 10. That's fast.
Yeah, figure 3C in their paper shows several examples of the MP function's output converging to its final, stable value within just those 10 iterations, which is incredibly fast for an iterative computational process. They also meticulously delved into the impact of bit precision, which is crucial because reducing the number of bits used to represent numbers can save significant chip area and power. As shown in Figure 4, the MP approximation maintains better precision for the same output bit width compared to standard quantization techniques. Even more importantly, any small unavoidable errors introduced by this approximation or by the use of fixed point arithmetic, instead of more complex floating point numbers, can be actively compensated for and minimized by the online learning mechanism, which we'll discuss shortly. This resilience is key.
So the learning helps fix the approximation errors.
In a way, yes. The authors found that for an n-bit inner product output, the quantized MP inner product requires a smaller input vector bit width due to using additions instead of multiplications, further enhancing efficiency, as detailed in Table 1.
That's a truly deep dive into the underlying math and hardware. It's clear they've engineered a brilliant way to make division and multiplication disappear. But if we connect all this back to the bigger picture, what does all this mean for the actual energy savings? We've talked about multiplications being the energy villain, but how much less energy does an MP-based computation actually consume compared to a traditional multiplication-heavy approach? Can you give us a sense of the scale of these savings?
The energy cost savings are quite dramatic, and the paper lays out specific equations to quantify this impact. Let's think about a traditional matrix vector multiplication, MVM, the bread and butter of many ML algorithms. If you're dealing with an m-dimensional vector in an m by m matrix, the total energy cost, C, scales with the square of the dimension m dou.
Okay, m squared. That grows fast.
Exactly. That's because you have m on or individual multiplications plus a slightly smaller number of additions. The equation is something like C equals m mani OEC plus m on m ACA, where Cm is the energy cost of a single multiplication and Ca is the cost of an addition. The key here is that m on or ECM term. It grows very, very quickly and dominates the total cost. Now compare that to the MP-based approximation for NVM. The energy cost, CMP, is calculated as m plus MAFER SECA plus MIR ACC.
Whoa, okay, break that down.
Don't worry about memorizing the formula, but let's look at the components. S is a sparsity factor, R is the number of Newton-Raphson iterations, which we know is a very small fixed number, like 10, and CC is the energy cost for a comparison operation, which is extremely low. The critical takeaway here is profound. CMP scales primarily with additions and comparisons rather than multiplications.
CM term.
Right. Remember earlier when we said an 8-bit multiplication is nearly 7 times more expensive than an 8-bit addition? Well, for an n-bit system, a multiplication itself requires roughly n equivalent full adders. This means the cost of a multiplication CM is proportional to n XEACA. So when you eliminate that CM term and replace it with operations that are only proportional to CA, the complexity scales dramatically better.
So it's not just a small optimization.
Not at all. It's a fundamental shift from quadratically scaling multiplication costs to roughly linearly scaling addition costs. This difference is like swapping a gas-guzzling truck for an electric bicycle when you're trying to save energy. The efficiency curve is completely different. This makes the MP approximation technique ideal for digital systems, because the implementation of adder and comparator logic is far simpler, requires significantly fewer transistors, and uses vastly fewer resources than an equivalent multiplier. It's a game changer for shrinking chips and extending battery life.
Those cost equations and your analogy about the truck versus the electric bicycle really drive home the point. This isn't just a small improvement in efficiency, it's a completely different scaling behavior, which, as you said, is exactly what you need for those desperately resource-constrained devices at the edge. So they've managed to create this incredibly clever multiplierless operation for the foundational arithmetic. Now, the big question is, how does this actually fit into an entire machine learning model? How do they build a complete MP kernel machine architecture that can make predictions or inference, and even more remarkably, perform online training, meaning it can learn and adapt on its own in the field? 3, the MP kernel machine architecture, inference and online training. So we've got this clever way to avoid multipliers for fundamental operations like calculating inner products. Now, the big question is, how does this actually get integrated into a functioning machine learning model like a kernel machine to make useful predictions about the real world?
That's the next logical step, right? Bringing the pieces together. For kernel machines, the decision function is the mathematical rule that determines the output or classification, like whether a room is occupied or not, traditionally involves inner products, often expressed as Fx, Fus W, WTK plus B. The researchers, using their MP approximation, reformulate this decision function Fx into a differential format. FMPX equals Z plus Z.
Okay, Z plus minus Z minus.
Exactly. And crucially, Z plus and Z are themselves MP functions of different combinations of weights, biases, and the kernel outputs. This means the entire inference process, from the moment input data comes in to the final prediction, remains completely multiplierless. Even the kernel itself, denoted as K, which acts as a similarity measure between input vectors. You can think of it like a sophisticated pattern matcher that tells you how alike two pieces of data are, much like a Gaussian function would in a traditional SVM.
So it's comparing the input to learned patterns.
Pretty much, yes. And that kernel, K, is also defined using an MP approximation. They even specify a companion K plus mixnat K. The beauty of this approach is that when you look at the complexity equations, comparing this MP kernel machine to a traditional SVM, the MP kernel machine's complexity is a mere fraction of what a traditional SVM requires.
A fraction. That's huge.
It is. This is a significant engineering claim, promising substantial reductions not just in power and hardware resources, but also potentially a massive increase in the speed of operation, which is critical for real-time edge applications. Imagine your device making decisions hundreds of times faster using a fraction of the power.
That's incredibly powerful for just making predictions or inference on the edge. But as we discussed earlier, many systems only do that. They just use a pre-trained model. What about genuine learning and adapting? This raises an even more important question. Can these multiplierless devices actually learn on their own and continually improve their understanding while operating in the field? That would truly be a game changer for enabling genuine autonomy at the edge.
You're absolutely right. This is arguably the most significant aspect of their entire work, taking it beyond just efficient inference. Why online training matters so much is that traditional offline training, where models are built in the cloud and then deployed, is simply not ideal for edge devices operating in the real world. These devices often exist in dynamic, ever-changing environments where conditions might shift, new data patterns emerge, or existing models simply become stale over time.
Like the lighting changes or a new object appears.
Exactly. The ability to retrain or adapt on the device itself, without constant connectivity to a powerful cloud server, becomes absolutely critical for true autonomy and long-term relevance. Imagine a smart camera learning to recognize a new pet or a new family member without needing a software update. The researchers developed an ingenious online training algorithm that utilizes a gradient descent approach.
Gradient descent, like rolling downhill to find the best answer.
That's a good way to think about it. It's basically an iterative optimization algorithm that helps the model learn by tweaking its internal parameters like weights and biases to minimize its errors. They chose a specific cost function, E, based on absolute differences between the predicted and true labels, essentially prediction positive, actual positive, plus prediction negative, actual negative. This specific choice, using absolute differences rather than squared errors, is crucial because it's easier to implement on hardware as we require fewer bits to represent the cost function. This directly contributes to its overall hardware friendliness and efficiency. And here's the truly brilliant multiplierless part. The gradient descent steps themselves, which are used to calculate how to update the weights, W plus AW, and biases, B plus AB of the model, also rely only on basic primitives.
No multiplications in the learning part either.
None at all. We're talking about simple comparators, shift operators, counters, and adders. This means the entire training process, from calculating the error to determining the changes to the model parameters, and then finally updating those parameters, is completely multiplierless. This is what truly differentiates this system from many other multiplierless inference solutions out there. It offers a fully self-contained, adaptable, and genuinely intelligent AI on the edge, capable of continuous learning without needing to phone home to a supercomputer. They also incorporated a sophisticated process called gamma annealing to learn and adjust that crucial hyperparameter, AIR1, in the MP functions.
Ah, the tuning dial, gamma.
Exactly. Recall is like the tuning dial for the MP approximation. This parameter is iteratively tuned based on changes in the cost function, as described in their algorithm 1. Think of it like the system constantly checking how well it's doing and then subtly adjusting its internal approximation method to perform even better. This allows the system to fine-tune itself and adapt to the specific characteristics of the data it encounters over time, optimizing its own internal workings. Furthermore, they highlight a key advantage. Because the gradients for learning are themselves derived using the MP approximation, the training process is more attuned to minimizing the error rather than mitigating the approximation itself.
Okay, what does that mean exactly?
It's subtle but important. It means the system isn't just tolerating the approximation. It's actively learning to compensate for it within its own framework, which ultimately leads to an improvement in the overall accuracy and robustness of the system over time. It's like teaching a student who learns with a specific type of learning difference. You don't just work around it. You teach them to learn within that framework, and they become incredibly proficient in their own way.
That's truly remarkable.
Yeah.
A fully multiplierless system, even for learning and adapting in the field, that's an enormous leap forward. So the theory is elegant, and the online training is a game changer. But how did the researchers actually build this multiplierless brain? Let's get into the nitty-gritty of their physical implementation. How did they bring this revolutionary concept to life on an actual chip, and what does its internal architecture look like?
The team meticulously implemented their proposed MP kernel machine on a commonly used low-power Arctic 7 FPGA.
An FPGA, that's a field programmable gate array, like a configurable chip.
Exactly. It's a type of integrated circuit that can be configured by a designer after manufacturing, making it incredibly versatile for prototyping and for edge applications where custom silicon might be too expensive. Their specific design supports up to 32 input features. Imagine 32 different sensor readings or data points, and a total of 256 kernels or internal patterns, all operating with a 12-bit data path, which they found to be an optimal balance of precision and efficiency. These parameters can be modified depending on the specific needs of the application, of course. A truly key feature of this design, crucial for its incredible efficiency, is intelligent resource sharing. They've managed to reuse the same underlying hardware resources for both training and inference.
The same circuits do both jobs.
Pretty much. If you were to look at a high-level diagram, like Figure 7 in their paper, you'd see that the only additional components specifically needed for the training functionality are a handful of red blocks. This elegantly demonstrates just how efficiently they've integrated continuous learning into the core inference hardware. It's like having a single, compact toolkit that can both build things and then teach itself how to build them better without needing a separate, massive factory for learning. The architecture itself is broken down into 4 distinct, highly optimized stages, which operate in a pipeline, much like an assembly line. This allows for continuous, high-throughput processing.
Okay, 4 stages. What do they do?
Stage 0 is the memory management unit. This stage acts as the gatekeeper for all incoming data. Imagine input samples arriving from sensors in the real world. These input features are stored in dedicated memory blocks called block RAMs or BRAMs. To ensure a smooth, continuous flow of data without any pauses, they use a clever ping-pong buffer system. While an incoming sample is being written into one memory block, the kernel computation from the next stage is simultaneously performed on the previously acquired sample that's already sitting in the other memory block.
So it's always busy processing something.
Exactly. Eliminating idle time.
Yeah.
Stage 1 is the kernel function computation. This is where the core MP approximation happens for the kernel itself, essentially, where the system calculates how similar the new input data is to the patterns it has learned. The architecture features an impressive 64 MP processing blocks that all work in parallel, simultaneously.
64 mini-brains working together.
You can think of it that way. Each of these blocks computes the MP function, following the algorithm we discussed, taking inputs serially and performing those 10 crucial Newton-Raphson iterations to quickly arrive at its approximation. The resulting similarity measurements, or K-vector, are then quickly stored in another set of ping-pong buffers ready for the next stage. Each of these MP processing blocks also has its own small, dedicated memory, allowing it to quickly access the support vectors it needs for its calculations. Stage 2 focuses on merging kernel function output, serving as a core inference pipeline. Here, the system takes the similarity measurements calculated in Stage 1 and starts to combine them to make a final decision. It uses 3 layered MP blocks. The first 2 blocks operate in parallel, calculating intermediate values called Z plus and Z based on the weights and biases. Then the third MP block takes these Z plus and Z values and normalizes them to produce P plus and P, which represent the final prediction or classification.
So this is where the actual answer comes out.
Yes, this stage is continuously processing the kernel outputs from Stage 1, rapidly generating predictions as new data flows through the system. Finally, Stage 3 is the weights and bias update module, which is entirely specific to training and learning. This stage is only active during the training cycle when the device is learning and adapting. It calculates the error gradients, essentially, how much the model's predictions were off and in what direction, and then updates the internal model parameters, the weights, W plus E and W at B plus B, using the multiplierless gradient descent steps we discussed earlier.
Still no multipliers here either.
Still 0 multipliers. This stage also includes the architecture for calculating the overall cost function and performing the gamma annealing process, allowing the system to self-tune. Crucially, all these computations in Stage 3 also use only adders, comparators, and shifters, maintaining the multiplierless integrity of the entire learning system. The updated weights are stored in dedicated memory, and biases are kept in fast registers. Because all these stages work in a pipeline fashion, once the initial data fills the pipeline, the system can continuously process new data and make new predictions or learn new patterns with very high throughput. It's a beautifully choreographed, highly efficient, and completely multiplierless dance of data.
It's clear that the design is incredibly intricate and thoughtfully engineered to eliminate multipliers at every single level, from basic arithmetic to a complete self-learning AI system. It's a real tour de force of hardware-software co-design. But of course, the ultimate test is how it performs in the real world. So let's look at the numbers. Does this revolutionary approach actually deliver on its promise? 4. The proof is in the performance, results, and discussion. So the technical details sound incredibly impressive, almost like pulling a rabbit out of a hat by eliminating multipliers, and the architectural design is clearly innovative. But what about the real-world impact? Does this multiplierless MP kernel machine actually deliver on its promise of superior power, performance, and area efficiency? What are the raw performance metrics? Let's talk brass tacks.
The results are truly compelling and I think speak volumes about the success of this approach. The implemented design is capable of operating at a maximum frequency of 200 megahertz.
200 megahertz. That's pretty quick for edge AI.
It's very respectable for an edge device, allowing for rapid processing. When we examined resource consumption on the Arctic 7 FPGA, Table 3 in the paper provides the concrete numbers. It uses 90874 LUTs, which are lookup tables, the basic logic blocks on an FPGA.
Okay.
0.9788 FFs, or flip-flops, which are memory elements, and 35 RAMs, or block RAMs, for larger memory storage. But here's the absolute killer feature, the direct and monumental consequence of its multiplierless design.
Yeah.
It consumes 0 DSP units.
0. Seriously.
0. For context, DSPs, or digital signal processors, are specialized high-performance blocks on FPGAs specifically designed to handle multiplications and accumulations very quickly. They're typically essential for any serious signal processing or machine learning on an FPGA. The fact that this system needs none drastically reduces both the chip area required and the power consumption, freeing up those valuable resources for other tasks or allowing for much smaller, cheaper chips. It's an unheard-of achievement in this space. In terms of energy and power, the system achieves an estimated energy consumption of just 13.4 picojoules per sample processed.
13.4 picojoules. That sounds incredibly low.
It is, and a total power consumption of 107 milliwatts. To put that 13.4 PJ sample into perspective, remember the 0.2 PJ for a single 8-bit multiplication. This entire complex system, including inference and online training, is processing an entire data sample with the energy equivalent of roughly 67 multiplication operations.
Whoa.
That's a truly significant reduction, especially when you consider that it includes both inference and online training capabilities. Regarding speed, Stage 1, which computes a 256 by 1 kernel vector, requires only 8 of 24 clock cycles. Even more impressively, the training stage itself, which is typically far more computationally intensive, consumes only 524 clock cycles.
Training is faster than inference.
Well, the training update cycle is very fast. Thanks to sophisticated pipelining, once the system is fully operational, it can essentially churn out one prediction or adapt its learning roughly every 8 or 24 clock cycles overall, leading to incredibly high throughput for an edge device.
0 DSP units, 13.4 picojoules per sample. Those are genuinely astounding figures, painting a picture of unparalleled efficiency. But the real question for our listener, who's maybe comparing this against other cutting-edge solutions, is how does this truly stack up against other machine learning systems out there, especially other SVM implementations that are also targeting these power-constrained edge devices? Is it just efficient, or is it the most efficient?
This is where the comparative advantages truly shine a spotlight on the team's achievement. The researchers rigorously benchmark their system against other advanced SVM implementations reported in the literature, as detailed in Table 2 of their paper. Their MP kernel machine consumes the least amount of energy of 13.4 PJ compared with similar SVM systems with online training capabilities.
The least energy.
This isn't just a minor improvement. It means longer battery life, smaller batteries, or the ability to run more complex tasks on the same power budget. But there's more. Not only is it the most energy efficient, but it also handles a higher input vector size of 32 features, meaning it can process more complex data. Yet, it uses lower RAM bits and, critically, 0 DSP units compared to other systems that might use dozens or even hundreds of DSPs for similar tasks.
Still amazing.
It also boasts the lowest number of training cycles, approximately 2054,000, which translates directly to significantly lower latency and higher throughput for online adaptation. Imagine a drone that can learn new visual cues in real time, or a medical implant that adapts to your body's subtle changes without needing a massive power source or a complex cooling system. This is what these numbers unlock. To drive the point home even further, they performed a direct comparison with a traditional SVM inference algorithm that is one purely for making predictions, not even training implemented on the same PY&Q board.
So apples to apples on the same hardware.
Exactly. Even this simplified linear kernel SVM consumed significantly more resources. It had higher power consumption, about double the LUTs, and shockingly, 192 DSPs compared to the MP kernel machine's pristine 0 DSPs.
192 versus 0.
Right. This stark contrast perfectly illustrates where the multiplierless design truly shines, fulfilling that critical need for a minuscule hardware footprint and extremely low power consumption on edge devices. In environments where every watt-hour of battery life and every square millimeter of silicon counts, this system isn't just an option, it's a revolution. It essentially makes what was previously a power-hungry, space-consuming operation into something almost negligible.
So the efficiency gains are undeniable, truly revolutionary for edge computing, painting a very clear picture of performance and power. But as a user or anyone investing in this technology, there's always that lingering skepticism. Does it still work? Is the accuracy comparable to traditional, more power-hungry systems? Or does this radical approximation come at a significant cost to the actual intelligence and performance? Is this having your cake and eating it too, or is there a trade-off?
That's indeed the million-dollar question, and the answer, happily, is reassuringly positive. You largely can have your cake and eat it too. The team meticulously validated their system using diverse, widely recognized datasets from the UCI-ML repository, ensuring its generalizability across different types of problems. They used an occupancy detection dataset, which classifies whether a room is occupied based on sensor readings like light, temperature, humidity, and CO2 levels, a classic IoT task.
Makes sense.
They also tested it on the activity recognition dataset, or RM, for tasks like distinguishing bending from lying activities, crucial for wearable health tech or smart home applications. And impressively, they even tackled the free-spoken digit dataset for speaker verification tasks using Mel frequency cepstral coefficients, or MFCCs, as features, which is a pretty complex audio processing challenge. For their methodology, they truncated the datasets to 256 inputs, which is what their current hardware supports, and used k-fold cross-validation.
Standard practice for validation.
Right. Standard, robust practice for reliable evaluation, where the data is split into segments, and the model is trained and tested multiple times on different segments to ensure the results aren't just a fluke. Crucially, they thoroughly investigated the impact of bit precision on accuracy, as shown in Figure 11. This is where the details really matter. They found that the system's accuracy remains remarkably stable down to 12-bit precision.
12-bit seems to be the sweet spot then.
It does. Below that, quantization errors, the slight inaccuracies introduced when you use fewer bits to represent numbers, begin to degrade performance noticeably. This is why they carefully and deliberately chose 12-bit precision for their hardware data path, striking that optimal balance. They explicitly state that the accuracy degradation between the full precision MATLAB model and the fixed point 12-bit RTL versions was minimal.
Minimal degradation, that's huge.
It's a monumental finding. It means that despite all the approximations and the complete elimination of multipliers, the system is performing almost as well as a theoretically perfect full precision version. And perhaps most importantly, as detailed in Table 4, despite being an approximation, the MP-based system achieved classification accuracy results that were consistently comparable to traditional SVM systems on the same datasets.
So you get the efficiency and the accuracy.
Pretty much. You're getting all those unprecedented power, performance, and area efficiency benefits without a significant compromise on the classification accuracy. It's incredibly powerful, proving that the system demonstrates its capability in classification tasks and with minor changes to the hardware can adapt to any application. It's an unequivocal success.
This truly feels like a breakthrough in how we fundamentally think about building intelligent systems for the future. We're talking about a paradigm shift. Outro. To recap, what we've seen today is the introduction of a novel, multiplierless MP kernel machine. This isn't just an incremental improvement on existing technology, it's a fundamental rethinking of how we perform machine learning on severely resource-constrained devices. It's custom designed for energy-efficient edge applications, capable of both making rapid predictions and, critically, performing online training learning and adapting on the fly, all on the very same compact hardware. We're talking about superior energy, power, and area efficiency, all while miraculously maintaining classification accuracy that's comparable to traditional, far more power-hungry systems.
And if we connect this to the bigger picture, the real-world implications are truly immense, verging on transformative. Imagine a future filled with truly autonomous, self-learning AI embedded at the very edge of our networks. Devices in remote locations, whether for environmental surveillance, critical medical applications woven into wearable tech, or intelligent smart infrastructure managing everything from traffic flow to agricultural irrigation. They could now adapt and improve over time without constant human intervention or the need for continuous, power-hungry cloud connectivity.
Intelligence everywhere, basically.
Exactly. This opens doors to a new era of intelligence that is truly ubiquitous, resilient, and deeply integrated into the fabric of our world, moving us closer to a future where AI isn't just a service in the cloud, but an ever-present, adaptive intelligence all around us. The paper even hints at future potential, discussing the possibility of fabricating this system directly into application-specific integrated chips, or ASICs.
Custom chips for this specific task.
Right. This would push the boundaries of power and area efficiency even further, custom designing the silicon to perfectly execute this multiplierless architecture. And perhaps most excitingly, they envision extending this multiplierless algorithm to even more complex machine learning systems, including deep learning, to leverage the same low hardware footprint. This could unlock unimaginable applications across countless domains.
This raises an important question for you to ponder. If we can fundamentally rewrite the arithmetic of AI to be this energy efficient, effectively making multiplication obsolete for these tasks, what previously unimaginable applications or entirely new paradigms of computing become possible when intelligence is literally everywhere, deeply embedded, self-sustaining, and constantly learning, all while sipping power instead of guzzling it? Think about that for a while. That's all for this deep dive. Join us next time as we continue to explore the cutting edge of science and technology.